Recall when we studied derivative before that we used the derivative idea to help investigate for extrema. And extrema can fall into two categories. We can talk about relative maximum and minimum points or absolute maximum and minimum points. Now, when it comes to graphs on a three-dimensional coordinate system, we might think of those extrema like this. Imagine that you take a sheet off of a bed, and on the bed you throw a few pillows around, and then you throw the sheet back onto the bed. Now, the top of the bed will be hilly like this, and you'll have some top points and some low points, and that's what extrema is all about. Now, the relative extrema idea in that environment is that we have a point where the value of z is the largest for a relative maximum. The value of z would be the biggest value of z, the biggest value that the function takes on in a neighborhood, in a circle around this little this spot. And a relative minimum would be a situation where the value of c is the smallest value, the value of the function is the smallest value within a neighborhood. So that's the idea. Now, in going through this process, we find critical points. Now, when we found critical points before, they were the zeros of the derivative function. They could also be the undefined values in the derivative function. Well, the same is going to hold true here, that we're going to find critical points, and those critical points are going to be the zeros of our two functions, our partial derivatives here that we talked about before. Now, we'll get to that situation in a moment, but I want to bring up one condition where, you remember when we were studying in the two-dimensional coordinate plane before, that we did have situations where we could identify a critical value and it didn't give us a relative maximum or minimum point. And that situation occurred like this. Here's the graph of it. That the graph comes down and it sort of levels off right here. And so the slope of the tangent line at that point would be 0, so it's a 0 of the derivative function. And then it continues to go down over here. So it's kind of it gives us a false sense that we have a relative maximum or minimum at that point. Well, a similar situation occurs in our development. We might have a situation where we think that we have a critical value. That is, we get a 0 on our we get zeros on our two functions, our two partial derivative functions. And we might say, oh, here we go. We've got a relative maximum and minimum point, so we just need to test for it. Well, it could happen that we have what's called a saddle point. This is kind of the false situation corresponding with the situation up there. Now, the saddle point looks like this. Notice that the graph here looks sort of like a saddle, and the saddle is high over here and high over here, and it dips in the middle. Now, that's what happens along the y axis. You see, in the y direction, it's we have a relative minimum at that point. But in the x direction, going across the saddle like this, we have a relative maximum point because the saddle goes down on the other side and down on this side. So saddle points are neither relative maximums nor relative minimums. Okay, here's how the process goes. We take a function in two variables and we calculate partial derivatives. So f in terms of x, the derivative in terms of x for our function turns out to be 4x plus 8. And then we calculate the partial derivative in terms of y. It turns out to be 2y minus 6. Now we calculate the zeros associated with this, the value of x that causes this expression to become 0. That would be x equals negative 2. And over here, the value of y that causes this to become 0 is a y of 3. Now this xy pair is the candidate for the position of a relative maximum or minimum, perhaps an absolute maximum or minimum point. So the critical point is f of negative 2, 3. And f of negative 2, 3 we find by replacing x with negative 2 and y with 3 in that expression up above, we find the value to be 3. So the z value corresponding to this x and y is 3. And the ordered triple would be negative 2, 3, 3. Okay, so that's our candidate at this point for maximum or minimum. Now, We can look at the graph to be able to tell what kind of situation we have here. And you'll see the graph of this one in your textbook, so it's easy to tell what kind of, I'm not going to tell you what kind of situation this is because we're going to figure it out. But we can use the second derivative, it turns out, to help us with the calculation. And before we get to the second derivative calculations here for this function, I want to show you what the whole process looks like. Now this is quite a departure from our study before. This is almost like looking at the discriminant in the quadratic formula for the first time or something like that, where we have some kind of relationship here involving partial derivatives. And we're calculating a number that we call d. And d is, well, let's see, it's the second partial derivative, this f of xx, and then f of yy. And each of those is evaluated at the candidate for the point. The candidate is AB. You see, it's a particular value for x and y here. That's why the AB is in here. And then minus f subscript xy of those same 2 points. So we have an expression for this second partial derivative, and within that expression we replace for these two specific values, and we evaluate, and then we square that number. So that's what this is all about. So it's a little bit involved here, but once we find d, we can make some determinations about, well, we hope to be able to make some determinations about relative maximum and minimum points. If d is positive, and if f of xx, f subscript xx, at this point is positive, then we have a relative minimum. If d is positive and this value is negative, then we have a relative maximum. And now notice, relative maximum when this is less than 0, minimum when this is greater than 0, doesn't seem to be, you see, we don't have a direct relation. We think maximum, gee, that's big. You see, so but remember, this is second derivative and all that kind of stuff. But it's a way to remember it. It's a way to recall it, is to think, gee, the relative maximum situation goes with a less than 0, a negative value here for this f subscript xx. Okay, now on the other hand, this is what happens if d is positive. What if d is negative? If d is negative, then we have a saddle point, you see, at that point AB and then f of AB. And if d is equal to 0, then the test fails and it gives us no information. All right, let's see what happens in our problem. Let's see what these values are, and let's plug in our problem. Well, we would go back over here and we would find these second partial derivatives. We need f of xx. So we take the f subscript x function. That's this guy right here. And then we find its derivative in terms of x. The derivative of this in terms of x is simply 4. All right, and then, now let me skip down to this one, the calculation for this one. F subscript yy. In the f sub y function, you see in this function, we are finding the partial derivative. You see it's the second partial derivative, and it's in terms of y. And so the derivative of this in terms of y is 2. And then we need an f of xy for that calculation over there. So f of xy, we use this first derivative in terms of x, and we find its derivative in terms of y. That's what this means. So we're using this expression, this function, and we want its derivative in terms of y. Well, in terms of y, these are constants, so they go out. So this becomes 0. Now we evaluate these at the critical point, at the critical value. And this function, this is a function, now it's a constant function, so it's rather trivial here, but evaluated at the point -2, 3 is 4. You see, it's still 4. And you might say, well, why is that? Well, it corresponds with our idea on a two-dimensional coordinate plane of this. Suppose I have, f of x is 3. That means that y equals 3. Now, a y line, recall, is a horizontal line up here at y equals 3. So y is 3 for every x. If x is 7, y is 3. If x is -5, y is 3. Y is 3 for every value of x. So we could say then that f of negative 5 is equal to g. It's equal to 3. You see, because no matter what value x takes on, the y value is going to be 3. Well, that's the idea here. We have a constant situation, and therefore, for f subscript double x of any two values, we're going to get 4 because that's a constant. In a similar way, this is going to be 2. In a similar way, this is going to be 0. All right, so with these values, then we can go plug in up here. Let's go. We have f double x subscript of our AB, and our AB here is negative 2, 3. And the value that we found for this was 4. And f subscript yy, second partial derivative, and so forth, turned out to be, for that point, 2. And the f subscript xy for our point here turned out to be 0. So this is 0 squared. So we have 4 times 2, 8 minus 0 is 8. So d is 8. D is positive. So d is positive in these two situations. Now we turn our attention to the value for f subscript xx of AB. Now we found that to be 4. Aha, that's positive. So if it's positive, if these two conditions hold, we have a relative minimum point. And so we determined then that this critical value gave us a relative minimum point. Let's find relative maximum and minimum points on the graph of this function. Now this function is a bit more complicated than the one before. The first partial derivative in terms of x is y minus x cubed. Notice it involves both letters here. The first partial derivative in terms of y is x minus y cubed. Now in the previous example, these equations were trivial. We could find a value for x and y in each of them outright. Now when this kind of situation occurs, we really need to solve this as a system of equations. You see, take these two and think of them as a system of equations. Now, what values for x and y will solve both of these at the same time? As a system of equations, now they're set equal to 0 here, so we can set the expressions equal to one another, or we can think of a substitution method. Either way is fine. I have solved this one for y, and now I'm going to put this y equals x cubed, replace the y over there, you see, with the x cubed, and we get this kind of thing. So I took that expression, replace the y with x cubed, and away we go. So we come down, we have x times 1 minus x to the 8th, and it turns out that x is equal to 0, x is equal to 1, or x is equal to negative 1. The y counterparts for each of these, though, we need to find in order to get those ordered pairs that are our critical values. When x is 0, well, we can come all the way up here and find the value of y when x takes on each of those values. When x is 0, y is 0. When x is 1, y is 1. When x is negative 1, y is negative 1. So the critical points are at 0, 0, 1, 1, and negative 1, negative 1. Now, in this process of evaluating for maximums and minimums, relative max and mins, we need the second partial derivatives. We need f sub xx of this function and f sub yy and so on. F sub xx, we look at the first partial derivative in terms of x, and we take the derivative of this in terms of x. And in terms of x, this is constant goes out. This is, let's see, negative 3x squared. So we have this. F sub yy means in this function, take its derivative in terms of y. Take its derivative in terms of y, and we have negative 3y squared. Now, f sub xy, that means in the first partial derivative function in terms of x, find the derivative of that function in terms of y. So here we're taking the derivative of this in terms of y. Oh, it turns out to be 1. These are the ingredients that we need to apply in the formula for finding d. So d has this. Here's the formula for d, and we're plugging into it. So we pop information in according to our critical points. So the point negative 1, negative 1. Now we're putting negative 1, negative 1 into the expression for this partial derivative function, and negative 1, negative 1 into this partial derivative function. And we find out that this rascal, when negative 1 replaces x and negative 1 replaces y in this function from the expression over here, it's negative 3. And this also is negative 3. And then over here we have minus 1 squared. Okay, so then collecting here, we find the value to be 8. Aha, D is positive. Now, if D is positive, we have a situation where we're going to have a maximum or a minimum, and it depends upon the value of this second partial derivative function at AB. And it turns out to be -3. Now, we used it in this calculation up here for D, but it's -3. So if it's negative, see, D was positive, this is negative, so we have a relative maximum point. All right, that's the conclusion that we make. And we run through the others in a similar way. Something interesting happens on this one. At the critical point 0, 0, when we evaluate for D, it turns out to be 0 times 0 minus 1 squared. Well, this is -1. So D, the value of D is negative, and we immediately skip over the idea of maximum or minimum, because as soon as we know that D is negative, we know we have a saddle point. All right, we know we have a saddle point. And then we come back and evaluate for the other critical point, the 1, 1, and once again, this turns out to be 8. And the value of this second partial derivative is negative, and that gives us another relative maximum point. Okay. Here's a situation where we can use this idea of derivatives, partial derivatives, and second partial derivatives. We don't have to. We can evaluate another way, but let me set the problem up this way. We have a plane that is intersecting our coordinate system, and the intersection points at the axes are here, here, and here. Those are just intersection points. The plane continues forever. And it's as though we have a little corner back in there, and this plane is kind of making a more or less a triangulation with that corner. And we'd like to find, and we have the equation of the plane, by the way. I have it written over here. We'll look at it in a minute. We have the equation of the plane, and we want to find the size of a box that will fit into this corner, a box where one corner is right there at the origin, and the opposite vertex of the box is touching this plane. Now, there would be many boxes that would have that characteristic. We want that one box that has a maximum volume. We want the box with a maximum volume. Wow. Now, let me see if I can draw this box. I don't know. I might get into big trouble with this, but let me just see. There's an art in doing this, and I for some figures I know that art, and in others I fail. But it's a matter of drawing parallel segments mostly, and so this would be the bottom of the box. Okay, and then the sides kind of come up, and we want something to parallel here. And I guess I'm showing this to you as much to help you learn to draw these things as for me to, let's see, I'm paralleling, all these verticals go up with the parallel to the z-axis, and they need to go up the same distance. And if you draw them up the same distance, you're in pretty good shape, because then you have the ingredients for the top of the box. And let me just see here. Well, that's not too awful bad. Okay. And now it's this corner right here at the top of that box that's touching this plane. All right. So we want of all the boxes that'll fit in that corner, and touch this plane, we want the one with the maximum volume. Well, how in the world do we deal with that? Well, we first take the equation of the plane, and here is the equation. Now notice it's just an equation involving 3 variables. But in order for us to think about this as a function, and we have seen the counterpart of this in the two-dimensional system. We have an equation involving 2 variables, x and y, let's say. What do we do with that in order to graph? We solve it for y. Well, here we're going to solve this for z. So we solve it for z. Kick the 3 z's to one side and all the other terms to the other side, divide through by 3, and we get this. Okay, now we have some value for z. Now remember, z is that up and down distance, sort of. It's a distance from the xy plane in this environment. And the volume of a box, you see in that corner, is going to be some distance or some length for x, some length for y, and some length for z. And we just need values for these. Well, we have a z. Z follows this prescription. And so it's xy times this, you see, coming down. And multiplying this out, we get this. Now we can go through that investigative process. You see, we need some critical values. We need values in the partial derivative in terms of x. You see, partial derivative in terms of y. And solving this as a system. Well, let's see, the partial derivative in terms of x. The derivative function of of v in terms of x. Well, we march through as we normally would. We get this expression. Derivative in terms of y. We get this expression. Now, these are complicated functions, and we set each of these equal to 0, and we solve as a system of equations. That in itself is a very difficult task. And I'm not going to get involved in that. We may have a chance to look at this problem again sometime, but theoretically or conceptually, we need to find the zeros associated with this system of equations. Okay, and it turns out that there are 4 of them. And they are these, 0, 0, 0, 6, 4, 0, and 4/3, 2. Okay, those are the critical values. Now, we could go through this second partial derivative business and evaluate d and all of that business. But you know, maybe there's another way. Gee, if these are candidates for values for x and y, then can't we find the value of z? Sure we can. Well, to find the value of z, if x and y are both 0, gee, we can use this expression right here. Let's come back over here and have a look at the expression. You see, if x and y are replaced with zeros, then z is equal to 8. So the z value is 8. If we replace x and y with 0 and 6, you see in here, then we can find a corresponding z value of the z that emerges when x is replaced with 0 and y with 6. It turns out to be 0 for z. And when x is 4 and y is 0, then z would be 0. And when x is 4/3, y is 2, z would be 8/3. Now, these are candidates for the sides of a box. Gee whiz, why did I even bother with all of this? Well, it doesn't make sense for a box to have a 0 value for one of the dimensions and a 0 value for it doesn't make sense for one dimension to be 0 and another to be 6. The box is infinitely small. You see, it doesn't have volume in these circumstances. The only one that's meaningful is this last one. The z value is 8/3. And now, so since this is the only one that's meaningful, let's calculate the volume of that box. Well, let's see. The volume is length times width times height, or x times y times z. The x value 4/3, the y value 2, the z value 8/3, 64/9, or 7 1/9 cubic units for the volume of the box.